Today, the diesel engine propels half the tonnage of all the world's shipping. Given good care, the diesel engine provides a maximum of effect on a minimum of oil consumption. The engineer will see to that. At the moment, he's checking the temperatures of exhaust and cooling water. His routine inspection takes him further down to the second platform with the intercoolers for charging air. Now he reaches the bottom, where his flashlight reveals the return piston cooling oil behind the sight glasses. To make a further study of the diesel engine, we leave the engineer and his instruments and put sight glasses on the engine from top to bottom. This reveals the movable parts: pistons, piston rods, crossheads, and connecting rod and crankshaft. This sectional view shows the function which the most important parts of the engine have to perform. In the upper part of the cylinder, an amount of fuel oil is burnt, which causes the temperature, and thereby the pressure, to rise in the combustion space. The gas pressure acts on the piston, from which the force is transmitted through piston rod and crosshead to the connecting rod, and results in a torque. The thermal energy has been converted into mechanical energy. In an arbitrary piston position during the working stroke, the crosshead is exposed to a vertical force from the piston rod and a force in the direction of the connecting rod, which together result in a horizontal force. This horizontal force must be transmitted to the engine frame, and for this purpose, the crosshead is provided with slide shoes supported on vertical surfaces, the guide faces on the engine frame. Powerful forces are at work in a big marine engine, and accordingly, the engine parts are of big dimensions. In the workshop, with people providing a natural yardstick, one receives a good impression of their size. So big must the crosshead slide shoes be in order to transmit the horizontal forces. The high points in the connecting rod bearing, which have been spotted by the contact with the crosshead pin, are scraped off in thin chips. To provide tightness against the high pressures, the piston is fitted with piston rings. The ring is fitted by a special tool which imparts an evenly distributed bending moment to it, thus preventing the danger of a permanent deformation. The cylinders are not easily overlooked either. The scavenge air ports are bored oblique to a diametal plane to set the scavenge air in rotation. The crankshaft is so big that to facilitate manufacture and installation, it's made in two halves, which are bolted together later. Each half is built up from a number of individual parts. Main bearing journals, crank webs, and crank pins. The crank webs are provided with counterweights. Let's look a little closer at the principle on which a two-stroke engine works. Fresh air is supplied by a blower. From the blower, it's conducted in a pipe along the engine to the scavenge air space around the cylinder. When the piston approaches the end of the downstroke, the exhaust valve opens, the scavenge air ports are uncovered, and fresh air flows up through the cylinder. Exhaust valve and scavenge air ports are then closed, and during compression, the air is heated for ignition of the injected fuel. The combustion increases the temperature and thereby the pressure which drives the piston. The exhaust valve opens, the pressure falls, and the combustion products are expelled. The air is again compressed. Fuel is injected, ignited. The gases expand. The exhaust valve opens, then the scavenge air ports. The cylinder is scavenged, and the cycle is repeated. The power developed by an engine depends on the pressure events in the cylinder. The pressure events can be recorded by means of an indicator connected to an outlet from the combustion space. The pencil is now moving in time with the pressure variations inside the cylinder. The drum carrying the paper is connected to the drive from the engine piston, its motion proportionate to the piston motion. The pencil records the pressure events during an engine cycle. The construction of the indicator is simple. Through a duct, the gas pressure is transmitted from the combustion space and acts on the indicator piston moving inside a small cylinder. The motion is resisted by a spring. This spring is exchangeable so that it may be adjusted to different pressure ranges. The motion is communicated to a lever at the point of which a pencil is fastened. The pencil is pressed against a drum, moving back and forth with the up and down motion of the engine piston. Thus, a curve is traced which shows the relation between the gas pressure in the engine cylinder and the position of the piston. The output of an engine is dependent upon the relation between pressure and volume in the cylinders during compression, combustion, and expansion. For each separate cylinder, the indicator traces a curve, the so-called PV diagram. The diagram shows that the pressure is almost equal to the scavenge air pressure when the scavenge ports are uncovered. The exhaust valve and scavenge ports are then closed. The air is compressed, and when the fuel is injected and ignited, the pressure will rise rapidly and remain at maximum during continued injection. After injection, the pressure in the cylinder falls to exhaust pressure, and during the exhaust period to scavenge air pressure. scavenging, compression, combustion, expansion, exhaust, and back to scavenging. The characteristic pressures are approximately a compression pressure of 54 kilograms per square centimeter, maximum pressure 66, exhaust pressure 8, and scavenge air pressure 1.75 kilograms per square centimeter. From the indicator diagram, the indicated output may now be computed. At an arbitrary position of the piston during the compression stroke, there is a certain pressure, P, acting on the piston top. If the piston travels a short distance further, corresponding to delta V, and if we ignore the minimal change in pressure, the amount of work done, delta A, will be given by the pressure multiplied by the change in volume, or P times delta V. This work is represented by the area below the part of the compression line corresponding to delta V. And the same applies to every single part of the compression curve. That is to say that the whole area below the compression line represents all the work that the piston must perform to compress the air in the cylinder. During the expansion, the piston pressure acts in the same direction as the piston is moving, so therefore the piston receives an amount of work, and it will be seen in the same manner as before that the amount of work received is represented by the area below the expansion curve. The amount of work transmitted to the piston during a full engine revolution must therefore be the difference between that delivered during the compression and that received during the expansion. In other words, it is given by the area between the curves. Thus, A equals sigma P multiplied by delta V. One could imagine the same area being produced by a compression stroke under atmospheric pressure and an expansion stroke with a constant pressure on the piston. This constant pressure, Pi, the mean indicated pressure, can be determined so that it gives the same area as in the actual diagram. In calculating the power, it is a great advantage to have to reckon only with a constant Pi during the expansion stroke, instead of the actual varying pressures in both the compression and the expansion strokes. The work in kilogram centimeters for one revolution will thus be A equals Pi multiplied by Vs, where Vs is the full stroke volume in cubic centimeters, and Pi the mean indicated pressure in kilograms per square centimeter. There is one working stroke in each revolution, so if we multiply by the revolutions per second, n over 60, we get the work in kilogram centimeters per second, that is to say, the power. Instead of Vs, we substitute the piston area multiplied by the stroke length, that is pi over 4 multiplied by d squared multiplied by s cubic centimeters. To arrive at the output in horsepower, 75 kilogram meters per second, we have to divide by 7,500, and we thus have the equation for computing the horsepower developed in each cylinder of the engine. To take an example, an engine with a Pi of 9.5 kilograms per square centimeter, a piston diameter of 84 centimeters, a piston stroke of 180 centimeters, running at 110 revolutions per minute, will have an indicated output of 2,300 horsepower per cylinder. The largest force acting on the piston is the highest combustion pressure less the atmospheric pressure on the underside of the piston multiplied by the piston area, or 65 multiplied by pi over 4 multiplied by 84 squared. That is 360,000 kilograms. The indicator diagram may also form the basis for computing the temperatures in the cylinder. Just after the scavenging, at the beginning of compression, the temperature is TO, the volume VO, and the pressure PO. From thermodynamics, we know that the pressure multiplied by the volume divided by the temperature is constant for an isolated amount of air, which is the case here in the cylinder, independent of the position of the piston, so long as the valve and the scavenge ports are closed. The equation can be rearranged to express the temperature T direct for an arbitrary position of the piston. The indicator diagram gives us the values that are to be substituted in the equation when computing the temperature for the top position of the piston. Substituting the initial temperature, 350 degrees Kelvin, the initial pressure, 1.75 kilograms per square centimeter, the initial volume, 950 liters, the pressure in top position, 54 kilograms per square centimeter, and the compression volume, 78 liters, we find the temperature to be 890 degrees Kelvin. The highest temperature occurs at the cessation of combustion. It is here found to be 1900 degrees Kelvin. In this way, the whole of the temperature curve may be calculated, right up to the moment when the exhaust valve opens. To get a better idea of what is happening, we will measure in degrees centigrade instead of degrees Kelvin. Already during compression, the temperature reaches the melting point of lead. During the first part of the combustion, the temperature reaches the melting point of aluminium. Shortly after that, the temperature reaches the melting point of cast iron. The high temperatures in the cylinders even exceed the melting point of steel. Combustion takes place so quickly, however, that there is not time for the high temperatures to be transferred to the cylinder wall. The temperature of the metal surfaces will not exceed the mean temperature of the process, about 620 degrees centigrade. Then again, the cylinder is made of cast iron, which begins to lose its strength already at around 300 degrees centigrade, besides which the lubricating oil will lose its lubricating ability if it becomes too hot. It is therefore necessary to provide efficient cooling, partly with oil or water led through the piston rod up into the piston itself, and partly with water circulating through the cooling jacket around cylinder and cylinder head. If a cooling water temperature of about 70 degrees centigrade is maintained, we can prevent the temperature on the inside of the cylinder wall from exceeding 300 degrees centigrade. This is possible because there is a drop in temperature as the heat passes from air to metal. The gas molecules are in violent motion inside the cylinder, but out near the wall they are slowed down and form an insulating layer. This causes a rapid fall in temperature at the boundary between gas and metal. Through the wall itself the temperature falls evenly, but as the heat flows into the cooling water, there is again a sudden drop in temperature owing to the retarded motion of the water molecules in contact with the wall. The mean temperature of the gas is 620 degrees centigrade, and the cooling water is kept at 70 degrees centigrade. It is possible to calculate a thickness of iron that offers the same resistance to heat flow as the boundary resistance between air and cylinder wall, and similarly a thickness of iron that corresponds to the boundary resistance between cylinder wall and water. As the drop in temperature through the entire homogeneous iron wall will occur evenly, the temperature of the original cylinder wall can be determined. These temperatures, which are calculated for the hottest point in the cylinders, explain why the materials are able to withstand the high combustion temperatures. The indicator diagram shows that the combustion in the cylinders occurs within a fraction of the time of a revolution. Within this fraction of a second, defined by the flashes, 50 grams of oil must be burned. A strong atomization of the oil is a condition for the short time of combustion. Without atomization, the oil will not ignite at all, even though the stream passes right through a flame. If the pump pressure is raised to 80 atmospheres, the oil is more finely atomized, but not enough to ensure reliable ignition. At a pump pressure of about 200 atmospheres, the atomization is so good that all injections are ignited. At the same pressure and continued injection, a flame is formed. But the flame soon dies out owing to lack of oxygen. Not until air is admitted through the pipe in the lower part of the picture can the flame be kept burning. The flame is formed some distance from the nozzle. The distance between nozzle and flame is about 4 decimeters. This corresponds to an interval of 1/400th of a second from the start of injection to the start of ignition, the delay period. In the hot engine, the ignition delay is approximately half. An experimental setup with a pressure chamber and a high-speed film camera taking 3,000 pictures per second will show the dependence of atomization upon the friction between oil droplets and air molecules. First, a vacuum is created in the pressure chamber, and the high-speed camera shows the appearance of the stream before it hits the bottom of the chamber. Then the vacuum is succeeded by a pressure of 3 atmospheres, and the high-speed camera registers the stream, which now has smaller droplets and a wider spray angle. The friction with the air molecules will be greater and atomization better when the oil is injected under high pressure. In the diesel engine, the pressure is produced by a fuel pump. The oil is taken in through a ring chamber, from where it is drawn out into the pump barrel, connected by a hole in the front of the plunger to a milled out recess in the plunger. The oil flows from the pump through a filter to a closed duct in the fuel valve. A heavy spring presses on the needle valve, which bars further access to the nozzle. The rise in pressure begins when the plunger has closed the inlet port. The oil presses on the conical end of the needle valve, lifts it a trifle, whereby the pressure area is increased and the needle snaps up. The oil now streams out through the nozzle holes at a very high velocity, resulting in a fine atomization. When the helical groove of the plunger passes the inlet port, the oil may flow freely back into the ring chamber during the continued movement of the plunger. The moment the plunger uncovers the inlet port, the oil pressure falls and the valve spring snaps back, pressing the needle into its seat so that it shuts off access to the nozzle. The helical groove on the plunger makes it possible to regulate the amount of fuel. If the plunger is turned in one direction, the useful stroke of the pump will be increased. If turned in the opposite direction, it will be reduced. Not all the energy contained in the oil results in mechanical work. The process incurs losses. The losses may be localized by drawing up a heat account, a heat balance. For instance, for this engine, which is erected on a test bed and provided with the necessary measuring instruments. The engine is receiving a final checkup and adjustment. Before the engine is started, cooling water and oil are turned on. Also, compressed air is needed for the starting. The control lever is moved, regulating the fuel pumps for increased injection. The speed of revolution is rising. The engine has now reached its full RPM, and we are able to find the power by means of the torque registered here on the dynamometer. If at the same time we measure the consumption, the air and cooling water quantities, and the temperatures, a heat balance can be drawn up. Let us imagine the engine as being isolated in a box. The energy admitted to and rejected from the box is ascertained for use in the heat balance. Whatever else happens inside the box is irrelevant to the heat balance. Energy is admitted from the fuel tank in the form of fuel oil. Thermal energy is carried away by the heated cooling water. Thermal energy is also carried away in the hot exhaust gases. And mechanical energy is absorbed by the dynamometer. If by weighing we find the amount of oil consumed in 10 minutes to be 450 kilograms, we are now able to calculate the thermal energy admitted per second. It will be 450 kilograms divided by 600 seconds multiplied by the calorific value of the oil, 10,000 kilocalories per kilogram, giving 7,500 kilocalories per second. The energy produced is determined by the speed of the engine, 110 RPM, and the brake torque registered on the dynamometer as 111,000 kilogram meters. The power will be the torque multiplied by the angular velocity. To obtain the result in kilocalories per second, we divide by 427. The result is 3,000 kilocalories per second. The energy carried away by the cooling water is determined by the temperature rise, 14 degrees centigrade, multiplied by the quantity of cooling water, found to be 123 kilograms per second. That is 1,720 kilocalories per second. In a similar way, the energy discharged with the exhaust gases is calculated from the rise in temperature, the amount of air, and the specific heat, and found to be 2,700 kilocalories per second. A clearer picture is obtained by converting the figures into percentages of the energy admitted. Drawing up the account, we see that there is a discrepancy of 1% on the loss side. This loss of energy is ascribed to the radiation of heat from the engine, which we have not been able to measure, plus unburnt constituents in the exhaust gas. It will be seen that the efficiency of the diesel engine is about 40%, which is more than can be attained with any other type of heat engine. The efficiency is a deciding factor in how far a ship is able to sail on a certain quantity of fuel. If a diesel motor ship can sail 2,000 nautical miles, a steam turbine ship will sail 1,500, and a ship with gas turbine 1,000 nautical miles on a given quantity of fuel. The engineer is still on his job, securing a long life for his engine by checking and testing. And one thing more, by knowing the meaning and function of every little detail of his engine.